Welcome everyone. Happy Friday afternoon. Thank you all for joining us for our Friday science seminar. We are very excited to be hearing from Dr. Mike Tylinski, assistant professor of chemistry with a focus in physical chemistry. Mike completed his PhD work at the University of Wisconsin in Madison, getting his PhD in chemistry with a focus on materials chemistry. Before that, he got his bachelor's degree with honors at Grinnell College. Before joining us on the faculty, he worked teaching at several institutions. We are delighted to have him join us, and we are very interested to hear about his research looking at how high concentration salt solutions can potentially be used to make improved batteries. Please join me in welcoming Dr. Taylor.
Thank you, Chris, and thank you all for coming. So the talk today is going to be interrupted by Zoom. Brought to you by Zoom. All right, we have. All right. It's going to be more of a background talk. So my first year, I have been working. It's mainly been figuring out what equipment and materials to buy, and then fighting with software. So those aren't as interesting, but the background is really cool. We're going to start with talking about what happens inside a lithium-ion battery. It sets up and motivates the research field that I'm going to be working in with SOU students, but also it's a really cool example of problem solving in science and engineering on a really complicated system. So the schematic that we're going to work through is up here of a typical rechargeable lithium-ion battery. The three big parts that we'll start talking about are the anode, which is the electrode on the left side in our schematic. On a regular battery, it's the part that's labeled with a minus sign. And then the cathode is the other electrode. It gets labeled with the plus sign. And then the electrolyte is the stuff in the middle. And we're going to go through and figure out or talk about what we use to make all those different parts and why. When our rechargeable lithium-ion battery is discharging, so when we're using it, lithium atoms give up their electrons. They do this at the anode. And then the electrons from the anode goes through an external circuit, so it does work for us. Powers our laptop or our smartwatches or our cars now. And then while the electron's going through that circuit, the lithium ions, which in our schematic are the little green circles, they move across towards the cathode. At the cathode, for our purposes, we have a cobalt atom that has a 4+ charge. It will grab that electron and become a 3+ charge. The same time that the cobalt atom is changing its charge, the lithium ion comes in and joins the cathode material, and the whole cathode charge stays the same with that process. When we recharge a battery, we're doing the opposite. So now we are pulling the electron off of that cobalt. Cobalt will go back to 4+. When that happens, the lithium ion leaves the cathode. Then the lithium ion goes through the electrolyte towards the anode side. The electron, we are doing work, so we're giving that electron a lot more energy and moving it over to the anode side, where it recombines with lithium and becomes neutral. We are also going to look at this voltage or electron energy diagram. So in electrochemistry, voltages are all relative to something. And so when we're talking about voltages today, we're going to be talking about them with respect to lithium metal. So the voltage associated with the reaction of lithium metal losing its electron, that's going to be our 0 point, and everything else is going to be with respect to that. So the electron in lithium metal is a pretty high energy electron. So it's the bottom of this voltage scale, but it's a high energy electron. And then our cathode, whatever our cathode ends up being, is going to be a situation where the electron's in a very low energy state. Okay? But that slightly, unfortunately, gets labeled as a positive. But think of this as the voltage that we get when the battery is discharging, as the electron goes from a high energy state to a low energy state, we get maybe 5 volts out. And then when I go to recharge the battery, I have to take that electron from the low energy state, the cathode, and I have to do work to pull it out and put it back into a high energy state. So I have to apply at least however many volts to do that. Okay. So this diagram is going to help us understand why we're using the materials we use in our batteries. Okay. So our anode is in a rechargeable lithium-ion battery is graphite. The same stuff that's in your pencil. Probably a different purity and kind of made to be really thin and that kind of stuff. But that's what we use. So it's just a bunch of carbon atoms. They arrange themselves into these hexagon shapes, and those hexagon shapes make layers, and lithium atoms can fit inside those layers. When we discharge the battery, the lithium atom gives up that electron to the graphite, and the graphite then sends it through the rest of it to the external circuit. So the voltage of the graphite anode is 0.1 volts versus lithium. So that means that the electron in lithium, when it's part of a graphite anode, is just a little bit lower in energy than if it was just pure regular lithium. So we're paying a slight penalty for using graphite. The ideal scenario would be using just lithium metal by itself. Okay? And also, those carbon atoms in the graphite, that's extra weight. We're making our battery heavier. So why are we using graphite? Why not just lithium? So if you use lithium as the anode in a rechargeable battery, what needs to happen, or we want to happen, when we recharge the battery, is that the lithium ions come back over, they join with the electron, they become neutral lithium metal, and it forms a nice flat sheet of lithium. Unfortunately, what does happen when you recharge a battery with a lithium anode is that the lithium atoms like to form these spiky crystals that we call dendrites. With enough recharge cycles, those dendrites grow and they reach across and they touch the cathode. At that instant, we have the anode, which has electrons that are really high in energy, touching the cathode, which is a material that has the possibility of a really low energy state for those electrons. And so all the electrons in the anode rush over to go join the cathode, which is a lower energy state. It releases a lot of energy really fast. It produces a bunch of heat, and it causes stuff in the battery to catch fire. We've actually tried this before. So in the late 1980s, there was a company in Canada called Moly Energy that had a commercial lithium metal anode rechargeable battery. They were used in the cell phones of the day. And so their battery is called the Moly cell, the brand name they gave it. And in 1989, a cell phone in Japan caught fire while somebody was using it, which caused some burns, and then obviously was a source of concern for everyone else with one of these cell phones. So it was a huge recall. Tens of thousands of phones had to be turned in. And then in the investigation process, they've figured out, hey, these dendrites are forming every time these batteries recharge, and they're shorting it out. So since then, as far as I am aware, we've not had any commercial lithium metal rechargeable battery. You can use lithium metal on a non-rechargeable lithium battery, but anything that recharges uses graphite as a anode. So the graphite itself has to be attached to some thin sheet of metal, so then we can make contact to it and then build it all into the battery housing. That thin sheet of metal is called the current collector. If you were looking really closely at that dendrite schematic, you may have seen a label of something that was aluminum. But on the anode side, our current collector is copper. But why couldn't we use aluminum? Aluminum is less dense than copper, would make our battery lighter, and it's definitely cheaper. But we can't use aluminum as the anode current collector. And that's because aluminum and lithium like to form an alloy. They mix together, the way lots of different metals mix together to form alloys. And if we're forming an alloy at the current collector, and then deforming that alloy when we discharge the battery, and the lithium ions go to the other side, and then keep doing that cycle again and again and again, we're going to make that aluminum film really brittle, because we keep putting atoms in and taking them out, and it's not a layered structure like graphite. The other problem with this is that the electrons in lithium atoms that are trying to make a alloy with aluminum are a little bit lower in energy than they are on our graphite anode. So when you go to recharge a battery and you have an aluminum current collector, the lithium ions preferentially go to the lithium, to the aluminum, and make that out. So that happens before the lithium ions go back into. So we can't use aluminum as the anode current collector. On the cathode side, we use lithium cobalt oxide as our cathode material. The cobalt oxygen make this layered structure, which is shown as these like red and white circles, and then the lithium ions kind of sit in the middle. The voltage of putting electrons in or out and putting lithium in and out of cobalt oxide is about 3.5 to 4 volts versus lithium. So this is setting what voltage we can get out of a battery. Okay? So when the electron leaves lithium and graphite and then goes and eventually joins the lithium cobalt oxide, we can get 3.4 to 3.9 volts out of that. And then when we go to recharge it, we need to apply at least that much voltage to send it backwards. Okay? That is not as high as that somewhat arbitrary 5 volts I put as a hypothetical cathode. I will tell you that there are cathode materials that would set up a 5-volt battery, but we don't use them. We don't use them because as you increase the voltage above 4 volts, which means you're lowering the energy of the electron in that material, we eventually start trying to pull electrons off of the solvent molecules or off of the anions that make up our electrolyte. And so using anything that creates a more powerful battery than about 4 volts causes electrolyte decomposition. So we can't use things beyond that. I picked lithium cobalt oxide as the material that was going to be in our battery, but there's actually a handful of different cathode materials. So people have made cathodes out of lithium manganese oxide. Lithium cobalt oxide by itself doesn't work as a durable cathode material, but if you mix nickel and cobalt and aluminum and oxygen in various ratios, that makes a good cathode material. You can do the same thing, just nickel, cobalt, and manganese. Lithium iron phosphate makes a cathode material. It's pretty sweet when that was figured out because we have lots of iron on Earth. And so this pie chart is an estimate of, in commercial devices, how much of different cathodes have been used, and a projection from, this was a group out of Argonne National. The current collector on the cathode side is aluminum. It's light and cheap, we want to use it, and because we're not trying to give lithium an electron on this side, it won't try and form an alloy with aluminum, so we can use it. Awesome. So let's look at the electrolyte in the middle. So the electrolyte has a solvent and then some ionic compound that's being dissolved, and that ionic compound has to involve lithium because that's what's getting moved back and forth. So what is exclusively used in commercial batteries so far is lithium hexafluorophosphate, LiPF6. So lithium has that positive charge, and then the PF6 has a negative charge. It's a fairly big anion, and then it has a bunch of fluorines on it that kind of like having an extra electron around. So that makes it a fairly stable anion. That means it will dissolve into our organic solvents. So we're not using water in our commercial devices. Organic solvents usually aren't good at dissolving ionic compounds, but having a big anion like that. Unfortunately, LiPF6 is really water sensitive. And so it's a little bit of a pain to deal with. but we have ways about that. And the reason why we really use it is it fixes the aluminum problem, the other aluminum problem that I haven't told you about yet. So the other aluminum problem is that aluminum, it's not that hard to take an electron away from it, actually 3. So the voltage for removing electrons from aluminum is only about 1.4 volts versus lithium. So lithium is a metal that easily gives up electrons. Aluminum's also pretty easy. Now, we use aluminum all the time in structures around us, and like we think of it as something that doesn't rust or doesn't corrode. And that's because a little bit of aluminum, when we have fresh aluminum and we expose it to the atmosphere, does corrode. It forms aluminum oxide. The difference between aluminum and iron is that aluminum oxide bonds very strongly to the aluminum metal underneath, and it protects it from any further corrosion. So that's why I kind of put this range of values, because with that aluminum oxide, it stabilizes the aluminum a little bit. But that protective aluminum oxide that lets us in every day use bare aluminum for stuff is not enough for the extreme voltages in our battery. But if we have LiPF6 as our electrolyte, when it's in the battery and we go through the first charge, a small amount of that LiPF6 breaks down on the aluminum current collector and makes a protective film that's even better than aluminum oxide is. People have studied a bunch and tried to figure out what that film actually is. At best, right now, we know it's some amount of lithium, phosphorus, and chlorine. But there's a thin, this is like atom, a couple layers of atoms thick film that's on the aluminum, but it means it doesn't corrode when we operate the battery. So that's why LiPF6 is the thing that is used in commercial batteries so far. Okay. I said that it decomposes with water, and so moisture is a problem for LiPF6. Moisture is also a problem for commercial batteries for other reasons as well. This picture from the Molly Energy people kind of shows what you have to do when working with things that are sensitive to moisture. This is what's called a glove box. So inside this box is some inert gas, it's probably argon. And then there's these rubber gloves that are sealed and attached, and you put your hand in through it, and then you have to work inside the box like that. And it's kind of annoying to do as a researcher. But then this also means that in a battery factory, all the assembly is done in some sort of air-free environment, whether it's done by humans or by robots or whatnot. So this adds to the complication of making batteries. Our solvent is actually usually a mixture of molecules. They're organic molecules, and I picked 2 examples for us to look at. So the first is diethylene carbonate. The ethylene refers to those 2 carbon chains at the ends of the molecule, here and here. And then this middle group of 3 oxygens and 1 carbon, that's the carbon. This liquid is okay at dissolving LiPF6. It's not viscous, it flows very well. Has a really low freezing temperature. Unfortunately, it's quite flammable. But we'll see why we still use it or similar molecules. The other molecule that I have on the board is ethylene carbonate. This is even better at dissolving LiPF6. It's not as flammable as DEC, but it's still flammable. It has, unfortunately, a high freezing temperature. Pure ethylene carbonate is a solid at room temperature. But it's really important because it fixes the solvent decomposition problem, another problem. It turns out that the electrons in our lithium and graphite anode are so high in energy that they try and put themselves onto our solvent molecule. So here in chemistry, that's a reduction. And so these electrons are so energetic that they will reduce, they will force themselves onto our solvent molecules and cause them to break apart. So we shouldn't be able to use these solvent molecules with this high energy anode material. Okay? But ethylene carbonate, if we have it in our electrolyte solution, a little bit of it breaks down on the anode during the first cycle of the battery and forms a protective film. This protective film is a little bit different than that one on aluminum. This protective film has atomic sized holes in it to let lithium ions move in and out so they can be discharged and recharged the battery, but it prevents, they're small enough holes that it prevents any other solvent molecules or anions from getting in and touching the graphite. Okay? So this film is called the solid electrolyte interface, or SEI, and it's been a big deal trying to figure out what it is, how to make better versions of it in the battery research world. So this is our schematic of the battery. I've added our SEI, and we have a bunch of different places where we either had to use a less ideal material like copper as our current collector or graphite as our anode, or we cheated and we used aluminum, even though it should corrode in the battery, but we have a protective film on it. There's also a bunch of other additives in the solution and a separator that tries to prevent the anode and cathode from touching if there's deformation to the battery. Those various additives try and make the battery less flammable, try and prevent you from overcharging the battery, but there's still problems. So we're going to touch on two problems. Quickly, we're going to touch on resources, and then we'll come back to it. But this is a graph of the abundance of different elements on Earth. The x-axis is just the element number. The y-axis is the abundance with respect to silicon. So the way this is set up is averaging over all of Earth. For every 1 million silicon atoms you find, how many atoms of a different type could you find them? Okay. This varies by location. But averaged over all of Earth. So lithium, the other thing to point out, this is a logarithmic scale. The 10 to the 6 up here is where silicon is. And so if you go down one major tick mark, that means it's an element that's 10 times less abundant. You go down two tick marks, that's 100 times less abundant. Down 3 is 1,000. So we're making really big jumps. So lithium is not like at the bottom, like say gold and platinum, but it's not all that abundant, and it's not one of our rock forming elements that's super common basically everywhere. Cobalt is also somewhat low on this graph, and so using things like iron or manganese was good. And so we're going to return to thinking, and copper, there's copper. Aluminum is more common than copper, part of what makes it cheaper. So those are good moves to make. So we will come back and think about using other elements instead of the ones that we're using so far. The other big problem is flammability, of course. Batteries are actually probably safer than they've ever been, but we're using them way more than we've ever been. So you have probably a lithium-ion rechargeable battery in your phone, in your smartwatch, in your iPad, in your laptop, in your car maybe, in your e-bike, in your scooter. And so because we have so many of them, even though they're getting safer, we're still seeing lots of fires just because it's a numbers game. And so there's lots of stories about there were Samsung Galaxy Note phones had problematic batteries, and the FAA just banned them from planes entirely. Like not even just couldn't be in your check bag, you couldn't bring it on at all. New York City just passed a bunch of legislation trying to improve kind of public understanding of battery safety issues, and then also requiring electronic sellers to follow certain rules. So flammability is what happens to cause these batteries to fail in such a way is that when there is mechanical damage to the battery, you either force the electrodes to touch each other when they shouldn't, or you cause some of those protective layers that we have to start coming off. If you overcharge a battery, that's what electrical abuse would be, you start surpassing that protection that's given you by the SEI or that's passivating layer that's on top of the aluminum. And then if any of these things are happening and unwanted reactions start happening, oftentimes they're giving off heat. And as things heat up, more damage ends up happening. Perhaps you just get a fire, perhaps it can become worse in terms of their explosion. And the exothermic reactions are happening. So the pictures are some vehicles that have suffered battery fires. As big as the Boeing 787 had some problems on batteries for a while back. So we have flammable solvents. We are dissolving ions. Water is really good at dissolving ions, and it's not flammable. Why aren't we using water? So the green box up there is the electrochemical stability window of water. It's showing us the voltage required to start adding electrons to water. It's pretty easy. So lithium and graphite definitely has enough energy to start dumping electrons onto water. The product of that is some hydroxide ions, but ultimately also forms H2 gas in the battery. You start adding electrons to the water. On the other side, how much energy it takes to start pulling electrons off of water is right up against where our cathode usually is. And then one of the products of pulling electrons or oxidizing water is forming O2 gas. Doesn't sound as scary as H2 gas, but forming gas of any type in a battery is bad, and we don't want to do that. So we can't use water. At least that's what everybody thought for really long periods of time. So a bunch of the review articles you've seen as references up on the side have said, oh yeah, no OHs, no molecule with an OH can be considered as a solvent for that. But in 2015, a group at the Army Research Lab and the University of Maryland kind of figured out that if they put ions, a ton of ions in the water and use that as the solvent, you could expand electrochemical stability with that. So up here is the graph of kind of the big kind of experimental result of their work. The materials they were using was water molecules, and then this was the salts or the electrolytes, the ionic compound they were using, called LiTFSI. The full proper name of it is long. But you have a ton of this, and what they're measuring in this graph here is they have some electrodes in the solution, and they are holding one electrode at a constant voltage and then taking the other one and changing the voltage at that electrode. So that's what this x-axis is the voltage at one of the electrodes. And as they move the voltage of the electrode towards, so this is moving up, so we're trying to pull electrons out of the solution. You eventually start measuring current, which is our y-axis. You start measuring current, it's a positive current if we're pulling electrons out of the solution. And then as we move the electrode voltage to the other side, closer to where lithium is, we're trying to dump electrons into the solution, and we get a current once you're able to start doing that. So where this current starts to tick up or down shows you when we started doing a chemical reaction in the solution. Okay. So they did this at a bunch of different solution concentrations. The zoom-ins are up here. The red line is the thing to pay attention to that's a lot flatter than the other ones. And that was when they had the solution dissolved. So on the scale, it says 21 molal. So it's over 20 molar, if that's a concentration unit you're used to. For everybody else, in Gen Chem labs, we are often working with solutions that are less than 1 molar. The limit of solubility for salt in water, sodium chloride, if I remember right, it's like 5 to 6 molar. You can't even get that high of concentration with most ionic compounds in water. But these things with big, weird anions are able to do that. And so the stability window went from about 1.3 volts in pure water to about 3 volts in this extreme concentration solution. So what's happening? The water molecules are seeing a different environment than they normally do. So in a normal solution, there's a group of water molecules that surround the positive ion. There's a different group that surrounds the negative ion. They form the solvation shell. Most of the other water molecules are just surrounded by other water. It's do a first approximation, kind of like there wasn't salt there. Okay? And so the voltage to pull electrons off or add electrons to that is not that dissimilar from just regular pure water. But in these extreme concentration solutions and kind of their schematic of their most concentrated solution, it looks like this. It's so much that we call it water involved. But every single water molecule is involved in trying to make that solvation shell around the cation or the anion. And so by being close to that charged particle, it changes the energy levels of the electron within the water molecule. Here in chemistry, we're changing the molecular orbital energies, making the bonding orbitals more stable. The anti-bonding orbitals are even higher in energy, so they're harder to access. So their version of the voltage diagram is up here. So regular water by itself has this stability window of only 1.23 volts. Moderately concentrated solutions, you can get about 2 volts in the window. But in their solution, they got to 3 volts. And then there's something special. They found in their prototype battery that they formed an SEI layer, that protective layer on the anode that lets the lithium ions through, but not anything else. It protects it from being reduced. That hadn't been done before with a water-based electrolyte solution. That only formed at their super high concentration. The lower concentration solutions, even though it's the same atoms and molecules involved, didn't form an SEI. So that helped boost the window towards 3 volts. They made a prototype battery. They had to use molybdenum sulfate as their anode, lithium manganese oxide as the cathode, and they ran at like 2.3 volts. That's not that close to the 3.8 volts that's in our commercial batteries, but it was a big paradigm change for, hey, we can consider water. One thing to note is that this is still, we're looking at voltages are quite high compared to our best anode, which is graphite with lithium in it, which is down at 0.1 volts. Eventually, this group, a couple years later, found that they could recoat, they could kind of put an SEI on the anode ahead of time and then assemble the battery, and they were able to like make a prototype that ran at 4 volts. It wasn't durable though. After about 50 or 60 cycles, it started degrading. Back to, so we've got water, it's an option. So let's go back to looking at different elements to make our batteries. So lithium's not super abundant on Earth. Other elements that are in the same column on the periodic table, like sodium and potassium, are really abundant and also pretty evenly distributed around the Earth. Okay? So lithium is kind of concentrated in a few spots. Sodium and potassium are everywhere. So elements in the same column on a periodic table often behave similarly. That's why we made the table to look this funky way. But it gives us a hint that maybe we might be able to just take sodium and take potassium and kind of swap them in and make a battery out of that. Some information, sodium's a bit heavier than lithium, and potassium's a bit heavier than that. The voltage of taking the sodium and giving up an electron is about 3.36 volts versus the 0 volts of lithium. So it's a bit of an energy penalty to use sodium. Potassium, 0.13 volts. So not as good as lithium, but a little bit better. So we would make a heavier battery if we use these things. That would actually be just fine for certain applications where the battery isn't moving around. The big one for this is grid storage. You have a whole bunch of really large battery packs that are storing energy that's produced by a solar farm or a wind farm. Those are intermittent renewable resources. And so when the grid then needs that energy, you can release it back when you want it. So is that an easy swap? Not quite. So for sodium, you can't use a graphite anode. Sodium atoms just don't want to go into graphite. There are alternatives that are really low energy anode materials. There are then problems to work on in terms of making an appropriate SEI that's really durable. The good news is that the cathode materials that we might use for a sodium-ion battery often are usually really abundant elements, like iron, carbon, and nitrogen. It's kind of maybe the most promising one. Potassium, weirdly, even though it's bigger, it will go into graphite. And so our schematic up here is the spacing between graphite layers. This is the spacing after you put some lithium ions in. This is the spacing after you put some potassium ions in. And so the gap between graphite layers got way bigger than it was before. And so that's kind of a problem. With lithium, the change is small enough that we don't have to worry about it. But with potassium, the graphite starts to fall apart after enough cycles. And then also the SEI that we might form on it starts to fall off because the graphite keeps expanding. So people are working on figuring out what kind of binders or glue you could use to try and hold the anode material together. The other nice thing about potassium, it's similar cathode materials as for sodium that use things like iron, which is super abundant. Both of them are compatible with lithium current or aluminum current collectors. They don't try and form an alloy with aluminum, so we can use that on both sides of the battery. Ultimately, there's just not as much R&D that's been done on these battery technologies yet, but that is picking up. So the big next steps in the field as a whole is trying to make more durable electrode materials, so cathodes that don't fall apart or anodes that don't fall apart after lots of cycles, and developing kind of passivating protective layers that are really durable. That kind of research is probably best done for organizations that have access to things like electron microscopes and things like that, because you really want to look at what's happening at the atom level on the surfaces of these materials. Another push is try and move away from fluorine. I didn't highlight it on our element abundance chart, but fluorine is not super high in terms of its abundance. And so it makes things kind of a bit more expensive. So these two possible potassium-based ionic compounds, this one for a given purity costs about $300 for 10 kilograms. This one is $300 for 5 grams. So things with fluorine's kind of a pain to work with synthetically, and then it makes things really expensive. Fluorine compounds are also often toxic to the environment and also to humans. A little bit of fluoride in our water is good, but beyond that, it starts having toxic effects on us and the environment. So moving away from that would be good. The problem is that the best protective layers that we've seen in batteries often involve fluorine atoms. Maybe there will be a compromise where we can make those protective layers ahead of time and then assemble the battery without any additional fluorine. There's a problem with the water and salt electrolytes. They end up being quite viscous. They're very thick liquids. They don't flow very well. This can hurt ion conductivity, how fast the ions move back and forth. That affects how fast you can recharge or discharge your battery. It's also a problem for assembling and making a battery. So if you imagine like one of those little watch batteries, a little 20, 32 cells or whatever, they're pretty thin, and that's the outside. So on the inside, the separation between the cathode and anode is really thin, and you need to fill it with a solution that needs to go in and wick in and cover all the surfaces really easily. That's a pain when you have something that's closer to honey than it is to water. So one alternative to this is possibly having a mixture of water, but then some of those organic solvent molecules were talked about before, and maybe that mixture will still not be flammable and still be stable at high voltages. And then we also want to try and predict or explain the behaviors that we're seeing in these liquids with computational models. Some of the challenges are that in quantum mechanics, when chemists try and look and understand the energy within a molecule, we try and look at just the one molecule by itself. We're in a regime where we have to pay attention to all the other molecules that are around it. That makes the problem harder to solve that. And then how things are moving in these solutions starts getting kind of funky. So sometimes conductivity is decoupled from viscosity, which is weird. People have seen, at least in some simulations, that water molecules will spin one way like this, but not spin the other way, that, because of these extreme, where people are still trying to figure it out. So the work that we're getting started in my lab, so some students are already getting started on this, and we will pick it up a lot more in the summer, is to measure the properties of these hybrid electrolytes. So what we're going to look at is water, and then we're going to mix it with organic solvents that come from biorenewable sources. So things like waste plant matters, like corn husks, stalks, and things like that. So one such molecule is up here. This is called gamma valerolactone, and it's within this family of organic molecules that are used as solvents that can be made from bioresources instead of oil, which is where most of our chemicals come from. And actually, this one's already commercial. So the stuff that Dave bought for me is already it comes from a bio feedstock. And it was cheaper than any of the other options. So that's super promising. And then we're going to be mixing that with sodium or potassium salts. And we're going to focus on these fluorine-free anions. And the things we want to measure are when I start mixing together these combinations of solvents and then anions, what are the stability windows at different concentrations? How conductive are these solutions? Have we made a solution that's stable across a wide range of voltages, but not viscous? And we will try and learn about the interactions between all these different molecules and try and explain what's happening. And maybe even do some flammability tests. I have to read a bit more about how that's done. But as far as I can tell, I think there's a certain common wick that you use. You soak it and you put it in a hood and you light it and see what happens. So we might get to do some of that. Yeah. So there's a lot of articles that have pictures of people with a lighter in a hood. And then there's a computational project too, where we're going to work on trying to model and predict and explain what's happening in these solutions. The experimental questions are being answered with these kind of techniques. So to understand what's happening with the stability window and to measure it, we're using something called cyclic voltammetry. That was the technique that I showed that graph from that 2015 paper. And with an instrument called a potentiostat, you have some electrodes in the solution and you're moving the voltage of one electrode and measuring the current through your circuit. And that's telling you when chemical reactions are happening. We're going to measure conductivity with a technique called impedance spectroscopy. The new potentiostat we're getting has the capability to do that. It's a 2-in-1 instrument. What you do is you apply a small voltage to your solution and you vary the voltage really fast. Well, sometimes really slow, sometimes really fast. It's at different frequencies. And you measure the current as a result of that oscillating voltage. And you fit that to models. You assume the solution is acting in some ways like a capacitor, in some ways like a resistor. And with those models that you build, one of those resistances tells you about the conductivity of the solution, how fast ions are moving within it. Viscosity could be measured the most simplest way with a tube, and you put the liquid in it and you measure how long it takes to flow out. So we will try that. Looking at interactions between molecules, we will use infrared or IR spectroscopy, and then eventually with the new NMR, NMR spectroscopy. So in IR, we're making the molecules vibrate, or atoms in the molecules vibrate. Those vibrational frequencies are sensitive to what else is around the molecule, in addition to what the atoms themselves are. And so then in NMR, we put our atoms, our solution, in a giant magnet. Nuclei react to the huge magnetic field in the NMR, but that reaction is actually also sensitive to what else is around. So it tells us about what's going on, what the neighbors are. And then flammability, I think we just light a wick. On the computational side, we are looking at doing molecular dynamics simulations. This is where I set up a virtual box. I put a bunch of virtual atoms or molecules in it. I calculate what the attraction and repulsion they are feeling to their neighbors. I let them move for a little bit. I stop. I recalculate all the forces. let them move again, and it lets us track exactly how everything is moving. The process kind of looks like that. Okay, right? In quantum mechanics, that lets us calculate the energy of each electron due to the effect of other electrons and other nuclei within that molecule. We will have to start doing a combined approach so we can feed a collection of molecules that represents an average snapshot of the solvent, because I have to look at more than one molecule at a time to get kind of realistic looks at the energies of the electrons and the molecular orbitals in these funky liquids. So that's the plan. We're already working on some of these things, but we'll pick up. Thank you.